All right, good morning. Last bit of information relevant to homework number 9, part 2. So what we're trying to do in chapter 5 is get you to A, apply the first law, and B, understand a bit of what goes on out there with different devices where a fluid flows through. I was talking to a civil engineering professor the other day, and he worked at the Air Resources Board, and he was talking, wow, that so much of the work just came from understanding the first law. Good thing to get down, and gives you a lot of insight into what's going on. So this last topic is on throttling valves, and that relates to refrigeration. That's probably one of the main applications of it, although throttling valves are all around. So let's talk about refrigeration really quickly. You know, how is it that, like, refrigerator, icebox, a cooling system for a building picks up heat and keeps the building cool? So as we've talked about before, if this represents your refrigerator in your kitchen, you know, it's around 40 degrees inside there, and it might be 75 in your kitchen, so heat's actually flowing into your refrigerator, and you got to remove that heat. And the way it's done is actually a pipe carries refrigerant through there. Now obviously the pipe's very, very small, just trying to idealize it and get an idea what's going on. And let me just give you an idea about how the numbers might work. Just give you an example. So we got some refrigerant going in there, and it could be R134A. There are other refrigerants that are used. Okay. A lot of times it comes in at a relatively low pressure. So for this problem, we're going to make it 35 psia. And ideally, it would come in as a saturated liquid, although it doesn't always happen. So I'm going to make it x equals 0.0. Okay. Now, when fluid goes through a pipe, it loses pressure, but if the pipe is properly sized, it's not a lot of pressure, so we could make the outlet pressure also about 35 psia. Okay. And I'm going to go ahead and give the typical outlet conditions. What happens is, as the refrigerant goes through there, heat goes into the refrigerant. If it is a saturated liquid and you add heat, well, saturated means about to boil, essentially evaporates as it goes through and it picks up heat. So many times these systems are adjusted so the refrigerant comes out as a saturated vapor, x equals 1.0. So hey, what I'd like you guys to try to do, just to get warmed up before we take a look at how do you make refrigerant like this, is figure out what this Q dot is. So I need to give you one more bit of information. We're going to assume this is steady state, and the refrigerant flow is 2 pound mass per minute. Okay, and there's a good first law problem. Steady state, open system. I would encourage you to stop the video, do a quick drawing of our system, which would be the refrigerant flowing through the pipe, and get all the ins and outs. I'm going to do that myself really quickly. So I'm drawing the pipe, and I'm thinking, okay, is there E mass in? Is there E mass out? Is there work in? Is there work out, etc.? And I'm going to come up with 3 heat transfers. Pardon me, 3 energy transfers, I should have said. 2 in and 1 out. Okay, so there we go. Refrigerant comes into this pipe. Okay, as it goes through, heat gets transferred in. Heat's always from higher temperature to lower temperature. This refrigerant is cool, and so heat flows in from the refrigerator into that pipe, and that removes this heat that came in. So we got heat coming in, that would spoil the food. Refrigerant flows through a pipe, heat goes into the refrigerant, and then that pipe exits with that heat. And this is the core of how a refrigerator or a refrigeration system works, or some sort of cooling, or most common cooling systems works. Okay, so then the question is, hey, can we solve for Q dot there? Well, that's easy enough. Just a couple quick notes. No work. We don't have any fans or compressors or turbines or anything like that going in the system. And Q dot would stand for the net heat transfer in. You'll see how the numbers work. All right, so the two things actually, besides working, figuring out what's going on with Q dot, we'd also like to get, hey, what's the refrigerant delta T as it goes through there? Refrigerant delta T. Okay, well, let's just take a look at the numbers really quickly and get T1 and T2. So 1 would be the inlet, 2 would be the outlet. T1, we're coming in as a saturated liquid at 35 psia, and so the temperature is going to be Tsat, and I'll go ahead and pull that from the charts. So you should have your table A12E. That's all you're going to need for the work in this video. And I'm going to 35 psia, and it's about 22.6 degrees. Really cool. Cool enough to keep your refrigerator cold. Okay, well, how about T2? How about T2? Well, it's coming out at the same pressure, and it is also saturated, a saturated liquid, vapor, but the temperature is going to be the same. It's also going to be Tsat. So T2 is 22.6 degrees Fahrenheit. Okay, so just like you to look at those numbers and ask yourself really quickly, hey, did that refrigerant pick up heat as it went through? Did it end up picking up heat? Okay, and some students might say, hey, no, it came in at 22.6, it went out at 22.6. The answer is actually yes, if you think about it. That refrigerant, as it went through, it actually evaporated, and the energy for the evaporation is this Q dot, and in fact, it ends up picking up a lot of heat. Okay, so we can pick up heat either through temperature change, if some sort of fluid picks up temperature, or we can pick up heat as evaporated. This component of the refrigeration system in your refrigerator is called the evaporator. So we're doing a good evaporator problem. All right, let's solve for Q dot, and that is just going to be an equation writing ins is equal to outs. So I'll do that really quickly, and you guys will be working on it yourself. Try to let you see a little bit. Okay, so there's my solution for Q dot. It's going to be m dot times the specific energy of the fluid at the outlet minus the specific energy at the inlet. All right, well, let's see if we can get E2 and E1 really quickly. So one thing that's going on, specific energy, remember, is enthalpy, kinetic energy, and specific potential energy. There's going to be no change in potential as we go through in this case. And for reasons that we can get into in more detail, there might be a bit of an increase in velocity, but if this pipe is sized correctly, the increase in velocity is minor. So what we're left with is the change in enthalpy. So taking a look at that, Q dot is equal to m dot times H2 minus H1. Okay, and we can get that from we can get the H2 and we can get the H1 from the tables. So I'll just fill the rest in. Give me just a second to read my tables. Okay, so those are the H's. I rounded off just a little bit. And if you just did the math yourself, 106 minus 19 turns out to be about 87. So we have 2 times 87, so what's that going to be, like 174 BTUs per minute. And that's a lot. That's a lot of energy removal. So from this 2 pounds per minute, that's a pretty slow flow actually going through this refrigerator, we pick up the equivalent energy of 174 matches a minute being removed from there, keeping that cool. Okay, so the heart of what we're trying to get at is, well, how do you actually make this refrigerant over here, which is 22.6 degrees Fahrenheit? So how do you make that, which is 22.6 degrees Fahrenheit? Okay, so let me do a little bit of sketching, and I'll give you the setup and what's needed. Okay, turns out one way you can do it is starting with about 90 degree Fahrenheit refrigerant, and you can make it into 22.6 refrigerant. So let's just imagine that we have a tank over here like this. Okay, and it's got R134A, say about at 90 degrees Fahrenheit, and also at a relatively high pressure. So also at a relatively high pressure. Sorry about my sloped tank, kind of hard to write. I should do better writing that way. Okay, so what we're going to try to do is make it into 22.6 degree Fahrenheit refrigerant, going from here to here. Okay, and it turns out the technique to do it is a throttling valve. If at the outlet of this tank we can have a device called a throttling valve and we set it just right, then we will end up getting 22.6 degrees Fahrenheit. Okay, so throttling valves, component device for which we should have some understanding and be able to apply the first law. All right, so throttling valves. So a bit about it, okay? Throttling valves are used in a lot of different ways. Really, the main thing they do is they lower pressure. So if you think about like a hose bib you have outside, if you open it up, the water just comes rushing out. Okay, what if you wanted the water to come out slowly? Well, you crank down on the faucet so that there's a restriction, and when the water goes through there, first of all, it comes out it backs up the water, and the water comes out at a slower rate. And secondly, it doesn't come out as high a pressure. So what you have is you have a small opening in the pipe, and that small opening actually restricts flow and lowers pressure. A throttling valve is any device which lowers fluid pressure as it flows through. Okay? So what we could do is we could model it, okay, as a pipe where we have an inlet, okay, and then we have some sort of valve in there, okay, which we can crank down on and just make a really small opening so that when our fluid goes through there, there's a lot of friction and it comes out with lower pressure. So we're going to have a fluid in there and a fluid out. Okay, we're going to have P1 be our inlet pressure and P2, and the main thing to understand is that P2 is a lot less than P1 with the throttling valve. That's why we use the throttling valve. Okay, could it operate at steady state? Could M dot in and M dot out be the same? Absolutely. That will be the case because we can't have more mass flow rate into something than out over a period of time. All right, so in short, that would be what's going on with throttling valves. What we want to do in addition is be able to come up with analysis using the first law. So I'm gonna just go ahead and take this throttling valve and draw it as a box that represents like a section of pipe. Hang on for a second, please.